Assalamualaikum and selamat sejahtera. My name is Nur Hafiza binti Ali. Today, our group want to present about statistic error, constant reference signal, and proportional controller gain. And my part is about introduction. Proportional integral derivative (PID) controller is a control machine that used to control a plant by depending on the feedback sensor. A statistic error is defined as a difference between the desired value and the actual value of a system when the response has reached the statistic error. We can calculate the statistic error of the system by using the final value theorem.
Hello everyone, my name is Janet Tijurin and I am going to continue our group's presentation by doing my part, which is the analysis of the relationship between the steady state error and a constant reference signal. First of all, I am going to briefly explain to you how we did our analysis by explaining the methodology of this particular analysis. First, we obtain the transfer function from the given journal, and from the journal we have obtained this transfer function. With this transfer function, we calculate our steady state error values with varying reference signal YRT from 10 to 100 radians per second in the steps of 10 and tabulate it. This is for us to compare it with our measured values later on. Once we have obtained the error values, we then construct a block diagram as such in MATLAB Simulink. I will briefly explain to you how we did our simulation later on. Once we have constructed this block diagram, we will vary the input from 10 to 100 in the steps of 10, and every error reading that we have obtained, we will tabulate it and compare it with our calculated values. Once we have compared and analyzed it, we will draw a conclusion out of the analysis. Now I am going to show to you how we did our simulation reading. This is the block diagram that we have constructed. This is the step input, which is responsible for our varying reference signal. This is our gain, which is going to be constant at 0.001 throughout the whole analysis. This is where we read the error reading, since here is where the error is going to happen, and this is the transfer function that we have obtained earlier, and this is the scope. So all we have to do is change the final value into this reference value that we want to use in order to find the value of the steady state error. So for example, we want to find the value of the steady state error at when the reference signal is at 10 radians per second. So we set it to 10 and then run the simulation. And then we may see here the error reading being 6.04, and we tabulate it in this table. And we continue doing this for the next 9 values and record every value into the table. So for one more example, let's use 50 radians per second as the input. We may read the value as 34.17. So that's how we did our steady state error reading for simulation. As you can see in this table right here, we have the values of the steady-state error, both our calculation and our measured values here, with our varying reference signal of 10 up to 100 and a constant gain value of 0.001. We obtained our measured values from the simulation as shown before, and for our calculated values, we obtained it through this equation. This equation we have obtained based on our observation of the block diagram being a unity feedback system. Thus, the equation, the reference signal over 1 plus Kp, and Kp is 0.4642. We obtain this value from the product of the transfer function with the gain value, which we then substitute in this equation, and thus giving us the value of Kp to 0.4642. So all we have to do is to substitute the reference signal and record every value that we calculate and tabulate it in this table. As we can see right here, there isn't much difference between the measured value and the calculated values. And as the reference signal goes higher, the steady-state error readings also goes higher. As a conclusion, we can conclude it in a visual representation from this graph. As we can see in this graph here, as the reference signal increases, the steady-state error also increases, thus indicating that the reference signal affects directly to the steady-state error. As the reference signal YRT increases, the steady-state error also increases. And that is our conclusion on the relationship between the steady-state error and the reference signal.
Assalamualaikum warahmatullahi wabarakatuh. My name is Siti Fadila binti Ibrahim. My ID number is EA19042. Today I would like to present about the methodology and result analysis. Figure 1 shows the closed-loop block diagram of a buck converter-driven DC motor. It consists of buck converter-driven DC motor, PID controller, block, and signal comparator. The output to control transfer function of the buck converter-driven DC motor at the nominal operating point is obtained as GS, this function. The block diagram in Figure 1 was constructed in MATLAB Simulink, which is Figure 2, and used the given transfer function in the block. The relationship of the steady-state error, reference signal, and proportional controller gain were observed. Steady-state error, reference signal, and controller gain will keep constant. Meanwhile, the reference signal will vary from 10 to 100 radians per second, and the calculated and measured value were recorded in Table 1. Relationship between steady-state error, controller gain, and reference signal will keep constant. Meanwhile, the controller gain will vary from 0.001 to 0.010, and the calculated and measured value were recorded in Table 2. This is a result of the Table 2, which is this is theoretical steady-state error that we calculate manually, and this is a result that we measure and we get from the MATLAB Simulink, and this is a controller gain Kp. We can see here that the controller gain keep increasing. Before that, I would like to show the manual calculating that we already calculate. Okay, this is a manual calculating, which is this is our function, and this is the formula YRS divided by 1 plus Kp GPS, and we substitute s equal to 0 in this function and we get this value. Okay. For this, YRT is equal to 1, keep constant, while Kp is keep increasing. So we just substitute the value of GPS Kp in this formula. So for the Kp 0.001, the steady state error is 0.6830. And we calculate the same way for Kp 0.002 and we get 0.5186. We continue calculate the Kp until 0.010. And this calculating, I already put it in the table 2. Now I would like to show how we get this measured value in MATLAB Simulink. Okay, so here we can see that this is our YRT, which is equal to 1. We keep constant, and this is our Kp. So I will show the example. We substitute our Kp is 0.001 and we run the simulation. So here we get 0.7447. So it's same like this table, and we try for 0.002. We get 0.4869. And lastly, we try for the 0.010. We get 0.1987. So same as this table. So here we can see that when a controller gain increasing, our steady state error is decreasing. From our analysis, the measure state steady state error not fixed as theoretical steady state error. When Kp value were increasing and constant while Rt equal to 1, the value of steady state error decreased and the controller gain Kp inversely proportional to steady state error.
Hi, my name is Nurhafiza binti Ali. I want to present about conclusion. From this lab, we'll be able to investigate the relationship between the steady state error, constant reference signal, and proportional controller gain. We noted that the higher the controller proportional gain, the lower the steady state error, and the higher the reference input, the larger the steady state error. That's all. Thank you.